Yeah, so thank you very much for inviting me to speak at this conference. It's an honor to be here. I met Tanya at the WCCM conference in Vancouver this summer, and he heard a version of this talk, and he encouraged me to give it here. It turns out I haven't changed the talk very much, so it's still a topology optimization talk. And this is because it turns out we didn't do anything very sophisticated. We didn't modify MFEM, or we didn't do anything very sophisticated to change MFEM. So it is a very sort of straightforward application of MFEM to solve PDEs. But I have to say, we used MFEM with great success, and we're very happy to be using MFEM for this project. So with that, let me continue. So the team that I represent is these four individuals here. We're all research scientists inside Autodesk Research. And this includes Mehran Ebrahimi, who's one of my colleagues. He's here in this meeting right now. And I should highlight that Mehran is a winner of last year's MFEM visualization contest. Well, thank you for that honor. Right, so the outline of my talk is as follows. So I'd like to give a motivation for the problem that we're trying to solve, and that motivation lies in the topology optimization of parts that belong to an assembly of larger parts. I'll show you what I mean by that in a moment. Then we'll talk about level set updates that preserve the interfaces between parts and assemblies. So this is the meat of our talk. And then we will show how we do simultaneous topology optimization of both the part and their interfaces to solve a topology optimization problem. So here's my motivation. So very often engineers are designing parts that belong to some larger context. So for example, the engineer might be designing this rocker structure, which I'm highlighting with my mouse here. It's the thing which connects the spring and damper component to the rods, which eventually connect to the wheel. So the engineer might be tasked with designing a more optimum structural part that functions as that rocker functions. And they might very well use topology optimization to do that, because topology optimization can create strong parts which can lightweight parts and make them optimally strong for their structural purpose. But there is an issue which I'd like to highlight, or a difficulty which I would like to highlight. So let's go into this. Spring damper suspension assembly with a bit more detail. So there you can see the rocker and the various components that it's attached to, and what those components themselves are attached to. And if we focus in on the rocker itself is a part which is connected to everything else in that assembly through what we're going to call in this talk interfaces. So for example, the rocker is a structural component. It connects to a push rod, it connects to a spring and damper unit, and it connects to the anti-roll bar. It also, not shown here, but it also connects to the chassis of the vehicle. So these connections occur at interfaces, and these interfaces can be as simple as welds, where one part is welded to another, fixed connection, or they can be revolute joints which permit relative movement, like in this example here. Now, if we look even closely at the rocker, so in isolation, we see that in a typical, in a typical scenario, that rocker would be in equilibrium. It would be under a set of forces which are in equilibrium, and there may be an inertial force as well. In any case, that part is being stressed or is being loaded in all sorts of different directions through its interfaces, and also potentially through an inertial force. These forces often act at the interfaces between the parts, and so therefore it's natural to seek the shape which has optimum performance under these loads. So the engineer who's designing this would want to use topology optimization to design for the load cases which come through the interfaces. And another natural idea is to be able to integrate the optimization of the interfaces with the freeform optimization of the part. So in other words, the locations of these joints and interfaces and the size might not be determined in advance, and it might be important to determine that through an optimization procedure to find the optimal locations and sizes and so on of the interfaces. But now, if you pose the problem in this way, then a key requirement emerges, which is that in the process of doing topology optimization, the nature, in quotes, of these interface regions have to be preserved. So just to say that in a different way, remember the topology optimization will alter the shape of this part. Well, it can't alter the shape of that circular aperture for the revolutoid very much, because then it ceases to function as a circular revolutoid. It must remain a circle. And in fact, what's important about that circle is its diameter, its height, and its orientation in space. So these would be the only parameters, let's say, that the optimization algorithm should be allowed to manipulate. So this is what I mean by the topology optimization must preserve the nature of these interfaces. So I'll just bring this slide up in its entirety here. So there has been related work for sure in the past 5 years looking at the joint optimization of shape and support locations and joint positions and so on. In the interest of time, I won't go into the details of these related works. You'll find those in a complete description of that in our paper. But let me move straight to our approach. So we would like to propose an approach for addressing this issue within the context of level set-based topology optimization. So we've chosen our geometry representation here. The geometry of our part is represented by a level set function. We would like to provide level set-based topology optimization with the ability to preserve the nature of assembly interfaces. And we would like to give parametric control to these interface regions. So whether they're loads and supports or joint interface regions. And this in turn will allow us to do simultaneous optimization of the free geometry as well as the interface geometry. So, right, so to remember that in order to so this leads us to a mathematical formulation of the problem we'd like to solve, which is we would like to minimize some objective function, which depends on the specific shape omega, subject to a constraint, which is that the boundary of omega contains interfaces of the specified nature. And we would like to minimize that performance function over all possible shapes and all possible allowed interface parameters. So I stress that it's a joint optimization here. So our methodology for tackling this problem is to introduce 3 separate ingredients. First is a representation for a level set representation with a little bit of an enhancement. We want to include interface data as well. So remember that you have a level set function. The 0 level set of that function is the boundary of the shape. Where that function is negative is the interior of that shape. And we would like to also maintain interfaces alongside this representation. Ingredient number 2 is going to be a method to update the level set function in such a way that the new level set function has interfaces of the same type. And then third, we would like to be able to choose this update based on a sensitivity analysis, so that in every iteration, not only is the shape and the interface is preserved, but the performance function gets better and better and better, which means that we'd like to obtain a descent direction to the objective function, and the consequence of which is that we will find eventually an optimal shape as well as an optimal set of interfaces when our algorithm converges. So with these 3 ingredients, we will have that ability. So let me now turn to these 3 ingredients one after another and just explain them in a tiny bit more detail. So let's start with the representation. So I'm going to say this is nothing very special. The level set function f will be as usual. So it simply encodes the boundary of the shape, and whatever is interior to the shape, f is negative. Whatever is exterior to the shape, then f is positive. But also we will just maintain sort of in a data structure fashion the fact that certain subsets of the boundary are tagged with an interface type. So the interface type might be a weld, a revolute joint, and that interface might have some simple parametric geometry like a location in space, an orientation in space with respect to some natural axes, and a size. And furthermore, whenever we update the level set function, we will be able to update the type and simple parametric geometry in accordance. So we're really just documenting and bookmarking and so maintaining the interface parameters as we go. So now that's simple, but now let's turn to level set updating. How do we update a level set function and its interface values such that the new level set function satisfies those properties as well? So to begin, let me just remind you how conventional levels updates are done in levels of topology optimization. So what's done is a velocity field is prescribed on the domain that surrounds the geometry of interest, and then you integrate that velocity field forward to move the domain. In other words, you solve the transport equation for the level set function, allowing it to be transported along the vector field for a short amount of time, and you determine that time typically by a line search procedure. And then the updated level set function is simply the transported level set function at the final time. Now, if you do this with just any level set function, with just any velocity field at all, what will happen is what you see in this image, which is that the circular aperture can very well get distorted since the velocity field vectors haven't been, perfectly adjusted to maintain circularity. So the new level set function will distort the interface. So we'd like to fix that. What we would like is that the velocity theta is such that the nature of the interfaces is preserved under transport. So in other words, if we start with a revolute joint with some radius and center parameters, then what we obtain after the movement is a new revolute joint with perhaps different radius and center, but still having radius and center. So one way to achieve this, quite simply, is to only allow rigid motions and scalings in the interface regions. So we're going to insist that our integrated motions be combinations of translations, rotations, and scalings. And note there's an order of operations which has to be respected here. And from that, we derive that velocity fields producing these motions must have a very specific form. They're of the form given at the bottom of this slide, with given translation parameter A, angular velocity vector B, and scaling factors, orthotropic scaling factors given by three components of a diagonal matrix C. So given A, B, and C, you can generate an allowed motion that we're going to allow within the interface region. So what we would like to do is update the level set function. So in order to update the level set function in an interface preserving way, what we would like to do is impose the constraint that theta equals the allowed velocity form with an appropriate A, B, and C in the interface regions. And once we have constructed theta in this way, then we solve the transport equation. And what you will find is that the free form part of the shape moves as usual, but where the constraint is imposed, circular regions remain circular, and interface geometry will preserve its nature as shown in this image here. Right. So yeah, so that's the plan. So now that's the plan for how we intend to modify the levels of transport procedure. But I still haven't told you how we're going to choose the update velocity. And as I said in my introduction, that's item 3 of my 3.3 ingredients, and this has to be done via a sensitivity analysis. So let me remind you that in topology optimization, you always want to choose the velocity field to cause a first order decrease in the optimization objective function. So the way you see what you need, how you understand that requirement is you do you expand, let's say you do a first order Taylor expansion, let's say, of the objective function in shape changes. And we know we have this well-known formula in topology optimization that the first order change of the shape is given as the surface integral of an object known as the shape gradient, which you can hand derive and compute and work with. It's the integral of the shape gradient against the normal component of the velocity field measured at the boundary. So therefore, in order to ensure that our theta velocity field is in the certain direction, we need that surface integral to be negative. So that's requirement number 1. We need the surface integral to be negative. If that is true, then updating the shape with that velocity will cause first order decrease of the objective function. And the other thing, as I said earlier, that we need theta to have the allowed form near the interfaces. But I'm also going to insist that A, B, and C, the translation, rotation, and scaling parameters, must also be chosen in accordance with 1.1 here, which is we have to choose the optimally correct A, B, and C, which allows the movement of that interface to also cause the, not to conflict, to also cause the objective function to decrease. So we've developed a procedure for doing this. So we're going to modify we're going to do this by modifying the Hilbert space velocity extension procedure, which is a common technique used in topology optimization to construct velocities for level set shape updates given sensitivity information on the boundary. The way this is done is you consider a velocity fields that are defined on a narrow band of the boundary. This is to ease computational burden. All you need to do is update the shape boundary by a very small amount, so you only need the velocity field defined in a small region around the boundary. And you choose a smoothing inner product on the Hilbert space of vector fields on this domain, and then we solve a variational problem, which in some sense projects the shape gradient onto this Hilbert space of vector fields in the smoothest possible way. And then you can prove quite simply that negative this solution of this variational problem is in fact a descent direction for the objective function. And this is in fact where MFEM comes in, because we will choose a very common smoothing inner product, which is the H1 norm of the velocity field. We'll try to keep the smoothest possible H1 vector field, which is the projection of the shape sensitivity information. And if you follow the procedure on the previous slide, you see that your velocity field has to satisfy this PDE, identity minus gamma times the Laplace operator equals to a right-hand side, with some essential and some natural boundary conditions. This is a PDE that we have to solve in that narrow band around the boundary, and we have done so using MFEM, and MFEM works brilliantly for our purposes here and interfaces quite nicely with the other application of MFEM, which is to solve the elasticity and structural problems that we look at inside the domain of the shape. Right, so here's how we modify the Hilbert space extension procedure to impose interface preservation constraints. So we're going to call the result of our procedure the constrained Hilbert space extension velocity. So what we do is we simply impose the constraint that theta equals the desired form inside each interface region. And now we minimize the resulting variational problem over all choices of vector fields, and this also means over all choices of translation, rotation, and scaling parameters. So this problem itself is also a PDE. It's a differential algebraic system. You end up solving a PDE for theta, and you also have some additional equations you have to solve for A, B, and C, such that all four of those objects provide you with a descent direction, or which optimize the constraint variational functional and give you a descent direction in theta for theta as well as for the A, B, and C's. There's a second step, which is there's a nuance here. Once we have this, I'll skip past this so you don't read it. But there's another nuance, which is once I have this vector field, I have to integrate it forward in time using a transport equation. We have to modify that a tiny bit, but I won't get into the detail there. The key detail here is we solve a PDE for theta in addition to A, B, and C, which are the constrained values in the interface region, which allows that velocity field to have the desired form in interface regions. So let me now move to a comparative example. So I'm going to compare the conventional Hilbert space extension method with the constrained Hilbert space extension, where we impose a translation constraint inside the revolute joint area. So the revolute joint area is this dashed circle. On the left-hand side, you can see the velocity vector fields of our ordinary HSE are, not particularly anything. They vary. They're variable inside that region. The sensitivity information is given in color. So the color here is the sensitivity information. So the velocity field should be large. So the right-hand side of that object should move very quickly, and the left-hand side of the object should move very slowly. And you can see that in the conventional HSE, the constrained region is kind of moving to the upper right, but it's going to be distorted. Now, if we turn to the right-hand picture, we have the similar sensitivity information, but now you see that the constrained region the motion there is very uniform. That's because we've imposed a translation constraint in the vicinity of that interface. And that translation constraint is that all the vector fields belong to the linear span of translation in X and translation in Y. So another thing to point out here is that the direction of translation has emerged from the optimization, from the sensitivity information through the Hilbert space, through the constrained HSE method. That upper right translation is an emergent property. All we imposed here was that the only movement that's allowed in that region is translation. The translation to the upper right was chosen because that's what optimizes or is a descent direction for the objective function. So here we see now the results of transporting the geometry with respect to both the conventional Hilbert space extension velocity and the constrained Hilbert space extension velocity. You see you have similar behavior in the free region, and that's expected. Nothing was really touched there. But in the constrained region, you have motion into the upper right corner, into the upper right direction by translation. And as a result, the circular region remains circular as it moves. And let me point out again, that upper right direction is chosen by the sensitivity analysis. It's not something we imposed. We just imposed the translation constraint. So now that we have this method to update shapes using this transport equation together with imposing constraints in interface regions, let me show you some applications of it to proper topology optimization problems rather than these toy examples. So we're going to look at some archetypical topology optimization problems. We're going to look at doing a structural optimization of an L bracket. We're going to I didn't mention this in the slide. I guess I shouldn't mention this in the slide, but it's a very simple topology optimization problem. We're going to minimize the compliance of the shape with respect to a single load. And that single load is going to be imposed on the interface region. So, and the green regions will be held fixed. So Dirichlet-boundary conditions on the green region. We're calling this a simplified load scenario because it's really a single part load scenario. I did give my introduction saying that we want to apply this to assemblies of parts, and this most definitely is not an assembly of parts. In an assembly, the load in the interface region would come from other parts, and that would be a reaction force coming from some bigger simulation. We haven't done any of that bigger simulation here, just because we want to focus our attention on the update procedure and show that it works. So this really is a simplified load scenario, which we're claiming is still representative of the sort of load you would experience in a proper multi-part assembly-based problem. So here is, the design optimization problem is to minimize compliance with the volume fraction constraint. We're going to allow the we're going to impose that the Dirichlet regions don't move at all, so the fixture points don't move at all, but that aperture can find its optimal location in space as long as it remains cylindrical, and as I said, we're going to impose a translation constraint to do that. So here is a topology optimization result showing you the various iterations, and in this first case, just to set the stage, we're not allowing that interface region to move at all. Zero motion there at all. That, of course, preserves circularity because nothing's happening at all. But now let's do that thing again. This time we allow the translation we allow the translation to exist and be non-zero. So what you see is the region in which the downwards pulling load is exerted, the interface region, is translating to a more optimal location based on iterative sensitivity analysis and constrained Hilbert space updates that build that motion into the extension velocity, the update velocity. So here's another setting. We're going to apply this to a cantilever. So it's a very simple cantilever problem. We're still going to minimize the compliance of a volume traction constraint, and we're going to impose additional restrictions. So first, the red interfaces, which is where the left-hand side of the cantilever attaches to its supports, are not allowed to move. But the orange box, which is where the load is applied, that is allowed to translate, and we're going to allow it to translate vertically. So we're doing this test case because it's kind of a benchmark problem. Not that we know an exact solution, but we have a rough idea what an exact solution. Well, we understand some properties that we would like the solution to have, which is we would expect that the point of application of the force is not optimally located right now. Optimally, it should occur at some symmetrical location between the two red boxes. So we kind of expect this thing to symmetrize itself, and sure enough, we obtain that kind of result. We obtain something which, given our volume constraint, has this sense that it's approaching to the Michel truss. So the location in which the load is imposed is translating upwards. All right, so some future work that we would like to consider. So we would like to consider more complicated parametric geometry and variations of the interfaces. We have a means now of incorporating motion constraints into the update velocity, and these motion constraints could in principle be more complex than rotations, translations, and scalings. Second, in line with the introduction to my talk, we would most definitely like to apply this to full assembly simulation. So where you have one part interacting with several neighbors, or more than one part co-moving and interacting with their neighbors. And we would like the simulation results to come from simulating the entire assembly, and we would like the forces that we're optimizing against to be reaction forces with respect to that simulation. So in other words, we'd like to move away from the toy scenarios that we've shown here to demonstrate our proof of concept. So in conclusion, we've developed this new shape update framework for level set-based topology optimization. It is intended for optimization of parts within assemblies, and as I said, that will be our future work here. This is a proof of concept. But in this proof of concept, we're using it to give parametric control, translation, rotation, and scaling over these interface regions. And that control allows us to find both optimal interfaces as well as optimal free-form geometry. So thank you. That's the conclusion of my talk.